Alright everyone, this is blog number 3, and today we are going to do chapter 2, which is The Patent Slave. This is 36 pages. What the fuck? Let's go. Bern, Switzerland, Friday, 17 March 1905. It was nearly 8 o'clock in the morning as the young man dressed in the unusual plaid suit hurried to work clutching an envelope. To a passersby, Albert Einstein appeared to have forgotten that he was wearing a pair of worn-out green slippers with embroidered flowers. At the same time, 6 days a week, he left his wife and baby son, Hans Albert, behind in their small two-room apartment in the middle of Bern's picturesque Old Town quarter, and walked to the rather grand sandstone building 10 minutes away. With its famous clock tower, the Zeitlogturm, and arcades lining both sides of the cobbled street, Kramgasse was one of the most beautiful streets in the Swiss capital. Lost in thought, Einstein hardly noticed his surroundings as he made his way to the administrative headquarters of the Federal Post and Telephone Service. Once inside, he headed straight for the stairs and the third floor that housed the Federal Office of Intellectual Property, better known as the Swiss Patent Office. Here, he and a dozen other technical experts, men in more sober, dark suits, labored at their desks for 8 hours a day, sorting out the barely viable from the fatally flawed. 3 days earlier, Einstein had celebrated his 26th birthday. He had been a patent slave, as he called it, for nearly 3 years. For him, the job brought to an end the annoying business of starving. The work itself he enjoyed for its variety, the many-sided thinking it encouraged, and the relaxed atmosphere of the office. It was an environment Einstein later referred to as his worldly monastery. Although the post of technical expert third class was a humble one, it was well paid and allowed him enough time to pursue his own research. Despite the watchful eye of his boss, the formidable Herr Haller, Einstein spent so much time between examining patents secretly, doing his own calculations, that his desk had been his office for theoretical physics. It was as if the ground had been pulled out from under one, with no firm foundation to be seen anywhere upon which one could have been built, was how Einstein recalled feeling after reading Planck's solution of the black body problem soon after it was published. What he sent in the envelope to the editor of Anleitung der Physik, the world's leading physicist's journal, on 17 March 1905 was even more radical than Planck's original introduction of the quantum. Einstein knew that his proposal of a quantum theory of light was nothing short of heresy. 2 months later, in the middle of May, Einstein wrote to his friend Konrad Habisch, promising to send 4 papers he hoped to see published before this year's end. The first was a quantum paper. The second was his PhD dissertation, in which he set out a new way to determine the sizes of atoms. The third offered an explanation of Brownian motion, the erratic dance of tiny particles, like grains of pollen, suspended in liquid. The fourth paper, Einstein admitted, is only a rough draft at this point and is an electrodynamics of moving bodies which employs a modification of the theory of space and time. It is an extraordinary list. In the annals of science, only one other scientist and one other year bears comparison with Einstein and his achievements in 1905. Isaac Newton in 1666, when the 23-year-old Englishman laid the foundations of calculus and the theory of gravity, and outlined his theory of light. Einstein would become synonymous with the theory first sketched out in this fourth paper, relativity. Although it would change humanity's very understanding of the nature of space and time, it was the extension of Planck's quantum concept to light and radiation that he described as very revolutionary, not relativity. Einstein regarded relativity as simply a modification of ideas already developed and established by Newton and others, whereas his concept of light quanta was something totally new, entirely his own, and represented the greatest break with the physics of the past. Even for an amateur physicist, it was sacrilegious. For more than half a century, it had been universally accepted that light was a wave phenomenon. On an heuristic point of view concerning the production and transformation of light, Einstein put forward the idea that light was not made of waves, but particle-like quanta. In his resolution of the black body problem, Planck had reluctantly introduced the idea that energy was absorbed or emitted as quanta in discrete lumps. However, he, like everyone else, believed that electromagnetic radiation itself was a continuous wave phenomenon, whatever the mechanism of how it exchanged energy when it interacted with matter. Einstein's revolutionary point of view was that light, indeed all electromagnetic radiation, was not wave-like at all, but chopped up into little bits, light quanta. For the next 20 years, virtually no one but he believed in his quantum of light. From the beginning, Einstein knew it would be an uphill struggle. He signals as much by including "on a heuristic point of view" in the title of his paper. Heuristic, as defined by the Shorter Oxford English Dictionary, means serving to find out. What he was offering physicists was a way to explain the unexplained when it came to light, not a fully worked out theory derived from first principles. His paper was a signpost towards such a theory, but even that proved too much for those unprepared to travel to a destination in the opposite direction to the long-established wave theory of light. Received by the Annalen der Physik between 18 March and 30 June, Einstein's 4 papers would transform physics in the years ahead. Remarkably, he also found the time and energy to write 21 book reviews for the journal during the course of the year. Almost as an afterthought, since he did not tell Habicht about it, he wrote a 5th paper. It contained the one equation that almost everyone would come to know, E=mc². A storm broke loose in my mind, was how he described the surge of creativity that consumed him as he produced his breathtaking succession of papers during that glorious barren spring and summer of 1905. Max Planck, the advisor on theoretical physics for the Annalen der Physik, was among the first to read On the Electrodynamics of Moving Bodies. Planck was immediately won over by what he, and not Einstein, later called the theory of relativity. As for the quantum of light, though he profoundly disagreed with it, Planck allowed Einstein's paper to be published, and as he did so, he must have wondered about the identity of this physicist capable of the sublime and the ridiculous. And then there's a break, and I will prepare myself mentally for the trauma I'm going to give myself. The people of Ulm, or mathematicians, was the unusual medieval motto of the city on the banks of the Danube, in the southwestern corner of Germany, where Albert Einstein was born. It was an apt birthplace on 14 March 1879 for the man who would become the epitome of scientific genius. The back of his head was so large and distorted, his mother feared her newborn son was deformed. Later, he took so long to speak that his parents worried he never would. Long after the birth of his sister and only sibling, Maya, in November 1881, Einstein adopted the rather strange ritual of softly repeating every sentence he wanted to say until satisfied it was word perfect before uttering aloud. At 7, to the relief of his parents, Hermann and Pauline, he began to speak normally. By then, the family had lived in Munich for 6 years, having moved so Hermann could open an electrical business in partnership with his younger brother Jakob. In October 1885, when the last of the private schools in Munich closed for more than a decade, the 6-year-old Einstein was sent to the nearest school. Not surprisingly, in the heartland of German Catholicism, religious education formed an integral part of the curriculum, but the teachers, he recalled many years later, were liberal and did not make any denominational distinctions. However liberal and accommodating his teachers may have been, the anti-Semitism that permeated German society was never buried too far beneath the surface, even in the schoolroom. Einstein never forgot the lesson in which his religious studies teacher told the class how the Jews had nailed Christ to the cross. Among the children, Einstein recalled later, anti-Semitism was alive, especially in elementary school. Not surprisingly, he had few, if any, school friends. I am truly a lone traveler, and have never belonged to my country, my home, my friends, or even my immediate family with my whole heart, he wrote in 1930. He called himself an Einspanner, a one-horse cart. As a schoolboy, he preferred solitary pursuits and enjoyed nothing more than constructing ever taller houses of cards. He had the patience and tenacity, even as a 10-year-old, to build them as high as 14 stories. These traits, already such a fundamental part of his makeup, would allow him to pursue his own scientific ideas when others might have given up. God gave me the stubbornness of a mule, he said later, and a fairly keen scent. Though others disagreed, Einstein maintained he possessed no special talents, only a passionate curiosity. The quality that others had, however, coupled with his stubbornness, meant that he continued to seek the answer to almost childlike questions long after his peers were taught to stop even asking them. What would it be like to ride on a beam of light? It was trying to answer this question that set him on his decade-long path to the theory of relativity. In 1888, age 9, Einstein started at the Luitpold Gymnasium, and he later spoke bitterly of his days there. Whereas young Max Planck enjoyed and thrived under a strict militaristic discipline focused on rote learning, Einstein did not. Despite resenting his teachers and their autocratic methods, he excelled academically, even though the curriculum was orientated towards the humanities. He scored top marks on Latin and did well in Greek, even after being told by his teacher that nothing would ever become of him. The stifling emphasis on mechanical learning in school and during music lessons with tutors at home was in stark contrast to the nurturing influence of a penniless Polish medical student. Max Talmud was 21 and Albert 10 when every Thursday he began dining with the Einsteins as they adopted their own version of an old Jewish tradition of inviting a poor religious scholar to lunch on the Sabbath. Talmud quickly recognized the inquisitive young boy as a kindred spirit. Before long, the two would spend hours discussing the books that Talmud had given him to read or had recommended. They began with books on popular science that brought to an end what Einstein called his religious paradise of youth. The years of the Catholic school and instruction at home by a relative on Judaism had left their mark. Einstein, to the surprise of his secular parents, had developed what he described as a deep religiosity. He stopped eating pork, sang religious songs on the way to school, and accepted the biblical story of creation as an established fact. Then, as he devoured one book after another on science, came the realization that much of the Bible could not be true. It unleashed what he called a fanatic free-thinking coupled with the impression that youth is intentionally being deceived by the state through lies. It was a crushing impression. It sowed the seeds of a lifelong suspicion of every kind of authority. He came to view the loss of his religious paradise as the first attempt to free him from the chains of the merely personal, from an existence which is dominated by wishes, hopes, and primitive feelings. As he lost faith in the teachings of one sacred book, he began to experience the wonder of his sacred little geometry book. He was still at primary school when his uncle Jakob introduced him to the rudiments of algebra and began posing problems for him to solve. By the time Talmud gave him a book on Euclid's geometry, Einstein was already well versed in mathematics not normally expected of a boy of 12. Talmud was surprised at the speed at which Einstein worked through the book, proving the theorems and completing the exercises. Such was his zeal that during the summer vacation he mastered the mathematics to be taught the following year at school. With a father and an uncle in the electrical industry, Einstein not only learned about science through reading, but was surrounded by the technology that its application could produce. It was his father who unwittingly introduced Einstein to the wonder and mystery of science. One day, as his son lay ill in bed with a fever, Hermann showed him a compass. The movement of the needle appeared so miraculous that the 5-year-old trembled and grew cold at the thought that something deeply hidden had to be behind things. The Einstein brothers' electrical business initially prospered. They went from manufacturing electrical devices to installing power and lighting networks. The future seemed bright as the Einstein notched up one success after another, including the contract to provide the first electric lighting for Munich's famous Oktoberfest. But in the end, the brothers were simply outgunned by the likes of Siemens, and AEG. There were many small electrical firms that prospered and survived in the shadow of the giants, but Jacob was over-ambitious and Hermann too indecisive for their company to be one of them. Being but not bowed, the brothers decided that Italy, where electrification was just beginning, was the place to start afresh. So in June 1894, the Einsteins were located to Milan. All except 15-year-old Albert, who was left behind in the care of distant relatives to complete the three remaining years of graduation. To complete the remaining years to graduation from the school he detested. For the sake of his parents, he pretended that everything was fine in Munich. However, he was increasingly troubled by the thought of compulsory military service. Under German law, if he remained in the country until his 17th birthday, Einstein would have no choice but to report for duty when the time came, or be declared a deserter. Alone and depressed, he had to think of a way out when suddenly the perfect opportunity arose. Dr. Degenhardt, the teacher of Greek who thought Einstein would never amount to anything, was now also his form tutor. During a heated argument, Degenhardt told Einstein he should leave the school. Requiring no further encouragement, he did just that after obtaining a medical certificate stating he was suffering from exhaustion and required complete rest to recover. At the same time, Einstein secured a testimonial from his mathematical teacher that he had mastered the subject to a level required to graduate. It had taken him just 6 months to follow in the footsteps of his family and cross the Alps into Italy. His parents tried to reason with him, but Einstein refused to go back to Munich. He had an alternate plan. He would stay in Milan and prepare for the entrance exams. The following October, of the Federal Polytechnicum in Zurich, established in 1854 and renamed Eidgenössische Technische Hochschule (ETH) in 1911, the Poly was not as prestigious. The Poly was not as prestigious as Germany's leading universities. However, it did not require graduation from a gymnasium as a preconditioning for entry. To be accepted, he explained to his parents, he just needed to pass its entrance exams. They soon discovered the second part of their son's plan. He wanted to renounce his German nationality and thereby remove the possibility of ever being called up for military service by the Reich. Too young to do it himself, Einstein needed his father's consent. Hermann duly gave it and formally applied to the authorities for his son's release. It was January 1896 before they received official notification that Albert, at the cost of 3 marks, was no longer a German citizen. For the next 5 years, he was legally stateless until he became a Swiss citizen. A renowned pacifist later in life, once he was granted his new nationality, Einstein turned up for a Swiss Army medical in 13 March 1901, the day before his 22nd birthday. Fortunately, he was found unfit for military service because of sweaty flat feet and varicose veins. Ew. As a teenager back in Munich, it was not the thought of serving in the army that bothered him, but the prospect of donning a gray uniform on behalf of the militarism of the German Reich, which he hated. The happy months of my sojourn in Italy are my most beautiful memories, was how Einstein, even after 50 years, recalled his new carefree existence. He helped his father and uncle with their electrical business and traveled here and there visiting friends and family. In the spring of 1895, the family moved to Pavia, just south of Milan, where the brothers opened a new factory that lasted little more than a year before it too closed. Although amidst the upheaval he worked hard to prepare, Einstein failed the Poly entrance exams. Yet his mathematics and physics results were so impressive that the professor of physics invited him to attend his lectures. It was a tantalizing offer, but for once Einstein took some sound advice. He had done so badly in languages, literature, and history that the director of the Poly urged him to go back to school for another year and recommended one in Switzerland. By the end of October, Einstein was in Aarau, a town 30 minutes west of Zurich. With its liberal ethos, the Aargau Canton School provided a stimulating environment that enabled Einstein to thrive. The experience of boarding with the classics teacher and his family was to leave an indelible mark. Jost Winteler and his wife Pauline encouraged free thinking among their $3.04. and dinner each evening was always a lively and noisy affair. Before long, the Vintlers became surrogate parents, and he even referred to them as Papa Vintler and Mama Vintler. Whatever the old Einstein later said about being a lone traveler, the young Einstein needed people who cared about him and he for them. Soon it was September 1896 and exam time. Einstein passed easily and headed to Zurich and the Federal Polytechnicum. And there's another break. Interesting. A happy man is too satisfied with the present to dwell too much upon the future, Einstein had written at the start of a short essay called My Future Plans during his 2-hour French exam. But an inclination for abstract thinking and a lack of practical sense had led him to decide on a future as a teacher of mathematics and physics. So it was that Einstein found himself in October 1896, the youngest of 11 new students entering the Poly School for Specialized Teachers in the mathematical and science subjects. He was one of the 5 seeking to qualify to teach maths and physics. The only woman among them was to be his future wife. None of Albert's friends could understand why he was attracted to Mileva Maric, a Hungarian Serb. She was 4 years older, and a bout of childhood tuberculosis had left her with a slight limp. During the first year, they sat through the 5 compulsory maths courses and mechanics the single physics course offered. Although he had devoured his little sacred book of geometry in Munich, Einstein was no longer interested in mathematics for its own sake. Hermann Minkowski, his math professor at the Poly, recalled that Einstein had been a lazy dog. It was not apathy, but a failure to grasp, as Einstein later confessed, that the approach to a more profound knowledge of the basic principles of physics is tied up with the most intricate mathematical methods. It was something he learned the hard way in the years of research that followed. He regretted not having tried harder to get a sound mathematical education. Fortunately, Marcel Grossmann, one of the 3 besides Einstein and Mileva, enrolled in the course. Fortunately, Marcel Grossmann, one of the other 3 besides Einstein and Mileva enrolled in the course, was a better mathematician and more studious than either of them. It would be to Grossmann that Einstein later turned for help as he struggled with the mathematics needed to formulate the general theory of relativity. The two quickly became friends as they talked about anything that might interest young people whose eyes were open. Only a year later, Grossmann must have been an astute judge of character, for he was so impressed by his classmate that he took him home to meet his parents. This Einstein, he told them, will one day be a very great man. It was only by using Grossmann's excellent set of notes that he passed the intermediate exams in October 1898. In an old age, Einstein could barely bring himself to contemplate what might have happened without Grossmann's help after he began skipping lectures. It had all been so different at the beginning of Heinrich Weber's physics course, when Einstein looked forward from one of his lectures to the next. Weber, who was in his mid-50s, could make physics come alive for his students, and Einstein conceded that he lectured on thermodynamics with great mastery, but he became disenchanted because Weber did not teach Maxwell's theory of electromagnetism or any of the latest developments. Soon Einstein's independent streak and contemptuous manner began to alienate his professors. "You're a smart boy," Weber told him, "but you have one great fault. You do not let yourself be told anything." When the final exams took place in July 1900, he came 4th out of 5. Einstein felt coerced by the exams, and they had such a deterring effect upon him that afterwards he found the consideration of any scientific problems distasteful to me for a whole year. Mileva was last, and the only one to fail. It was a bitter blow for the couple, who were now affectionately calling each other Johanzel, or Johnny, and Doxerel, or Dolly. Another soon followed. A future as a schoolteacher no longer appealed to Einstein. 4 years in Zurich had given rise to a new ambition. He wanted to be a physicist. The chances of getting a full-time job at a university were slim, even for the best students. The first step was an assistant's position with one of the professors at the Poly. None wanted him, and Einstein began searching further afield. Soon I will have honored all physicists from the North Sea to the southern tip of Italy with my offer, he wrote to Mileva in April 1901 while visiting his parents. One of these honored was Wilhelm Ostwald, chemist at the Leipzig University. Einstein wrote to him twice. Both letters went unanswered. It must have been distressing for his father to watch his son's growing despair. Hermann, unknown to Albert then or later, took it upon himself to intervene. Please forgive a father who is so bold to turn to you, esteemed Herr Professor, in the interest of his son, he wrote to Ostwald. And though all those in position to give a judgment in the matter praise his talents, in any case I can assure you that he is extraordinarily studious and diligent, and clings with great love to his science. The heartfelt plea went unanswered. Later, Ostwald would be the first to nominate Einstein for the Nobel Prize. Although anti-Semitism may have played a part, Einstein was convinced that it was Weber's poor references that were behind his failure to secure an assistantship. And as he grew increasingly despondent, a letter from Grossmann held out the possibility of a decent, well-paying job. Grossmann Sr. had learned of Einstein's desperate situation and wanted to help the young man whom his son held in such high regard. He strongly recommended direction of the Swiss Patent Office in Bern. When I found your letter yesterday, Einstein wrote to Marcel, I was deeply moved by your devotion and compassion, which did not let you forget your old luckless friend. After 5 years of being stateless, Einstein had recently acquired Swiss citizenship and was certain it would help when applying for the job. Maybe his luck had changed at last. He was offered and accepted a temporary teaching job at the school in Winterthur, a small town less than 20 miles from Zurich. The 5 or 6 classes Einstein taught each morning left him free to pursue physics in the afternoon. I cannot tell you how happy I would feel with such a job, he wrote to Papa Winterthur shortly before his time in Winterthur ended. I have completely given up my ambition to get a position at the university, since I see that even as it is, I have enough strength and desire left for scientific endeavor. Soon the strength was put to the test when Mileva announced that she was pregnant. After failing the Poly exams a second time, Mileva returned to her parents in Hungary to await the arrival of the baby. Einstein took the news of the pregnancy in his stride. He had already encountered thoughts of becoming an insurance clerk, and now vowed to find any job, no matter how humble, so that they could marry. When their daughter was born, Einstein was in Bern. He never saw Lieserl. What happened to her, whether she was given up for adoption or died in infancy, remains a mystery. In December 1901, Friedrich Haller wrote to Einstein asking him to apply for a vacancy at the patent office that was about to be advertised. The long search for a permanent job seemed at an end as Einstein set off his application before Christmas. All the time I rejoice in the fine prospects which are in store for us in the near future, he wrote to Mileva. Have I already told you how rich we will be in Bern? Convinced that everything would be settled quickly, Einstein quit a year-long tutoring job at a private boarding school in Schaffhausen after only a few months. And that's the break. My neck is killing me, man. It's like actually burning. Yeah, let me just moan my sorrows away. That's how it works, right? goodness. I feel so bad for my throat, but I gotta get through this, man. Alright. Bern was home to some 60,000 people when Einstein arrived during the first week of February 1902. The medieval excellence of the medieval elegance of the old town quarter had changed little in the 500 years since it had been rebuilt following a fire that destroyed half the city. It was here that Einstein found a room in Gerechtigkeitsgasse, not far from the city's famous bear pit. Costing 23 francs a month, it was anything but the large, beautiful room he described to Mileva. Not long after he unpacked his bags, Einstein went down to the local newspaper to place an advert offering his services as a private tutor of mathematics and physics. It appeared on Wednesday, 5 February, and offered a free trial lesson. Within days, it paid off. One of the students described his new tutor as about 5'10", broad-shouldered, slightly stooped, a pale brown skin, a sensuous mouth, black mustache, nose slightly aquiline, radiant brown eyes, a pleasant voice, speaking French correctly but with a slight accent. A young Romanian Jew, Maurice Solovin, also came across the advert as he read his newspaper walking down the street. A philosophy student at Bern University, Solovin was also interested in physics. Frustrated that a lack of mathematics was preventing him from gaining a deeper understanding of physics, he immediately made his way to the address given in the newspaper. When Solovin rang the bell, Einstein had found a kindred spirit. The student and tutor talked for 2 hours. They shared many of the same interests, and after spending another half-hour chatting in the street, they agreed to meet the following day. When they did, all thoughts of a structured lesson were forgotten amid a shared enthusiasm for exploring ideas. As a matter of fact, you don't have to be tutor in physics, Einstein told him on the third day. What Solovin liked about Einstein, as the two quickly became friends, was the care with which he outlined the topic or problem as lucidly as possible. Before long, Solovin suggested that they read a particular book and then discuss it. Having done the same with Max Talmud in Munich as a schoolboy, Einstein thought it an excellent idea. Soon Konrad Habicht joined them, a friend from Einstein's aborted stint teaching at the boarding school at Schaffhausen. Habicht had moved to Bern, to complete a mathematics thesis at the university. United for their enthusiasm for studying and clarifying the problems of physics and philosophy for their own satisfaction, the three men started calling themselves the Academy Olympia. Even though Einstein came highly recommended by a friend, Haller had to make sure he was capable of doing the job. The ever-growing number of patent applications for all manner of electrical devices had made the hiring of a competent physicist to work along his engineers a necessity rather than a favor from a friend. Einstein impressed Haller sufficiently to be provisionally appointed a technical expert third class with a salary of 3,500 Swiss francs. At 8 in the morning on the 23rd June 1902, Einstein reported for his first day as a respectable federal ink pisser. As a physicist, Haller told Einstein, you haven't a clue about blueprints. Until he could read and assess technical drawings, there would be no permanent contract. Haller took it upon himself to teach Einstein what he needed to know, including the art of expressing himself clearly, concisely, and correctly. Although he had never taken kindly to being instructed as a schoolboy or student, he knew that he needed to learn all he could from Haller, a splendid character and a clever mind. One soon gets used to his rough manner, Einstein wrote. I hold him in very high regard. As he proved his worth, Haller likewise came to respect his young protege as a prized member of his staff. In October 1902, aged only 55, his father fell seriously ill. Einstein traveled to Italy to see him one last time. It was then, as he lay dying, that Hermann gave Albert his permission to marry Mileva, a prospect that he and Pauline had long opposed. With only Solovin and Habicht as witnesses, Einstein and Mileva married the following January in a civil ceremony at the Baron Registrar's office. Marriage is, Einstein said later, the unsuccessful attempt to make something lasting out of an incident. But in 1903, he was just happy to have a wife that cooked, cleaned, and simply looked after him. Mileva had hoped for more. The patent office took up 48 hours a week. From Monday to Saturday, Einstein started at 8 o'clock and worked until noon. Then it was lunch either at home or with a friend at a nearby cafe. He was back in the office from 2 to 6. It left 8 hours for fooling around each day. And then there's also Sunday, he told Habicht. It was September 1904 before Einstein's provisional position was made permanent with a pay rise of 400 francs. By the spring of 1906, Haller was so impressed with Einstein's ability to tackle technically very difficult patent applications that he rated him one of the valued experts at the office. He was promoted to technical expert second class. I will be grateful to Haller for as long as I live, Einstein had written to Mileva soon after moving to Bern in the expectation that a job at the patent office would sooner or later be his. And he was. But it was only much later that he recognized the extent of the influence that Haller and the patent office exerted on him. I might not have died, but I would have been intellectually stunted. Haller demanded that every single patent application be evaluated rigorously enough to withstand any legal challenge. When you pick up an application, think that anything the inventor says is wrong, he advised Einstein, or else you will follow the inventor's way of thinking, and that will prejudice you. You have to remain critically vigilant. Accidentally, Einstein had found a job that suited his temperament and honed his abilities. The critical vigilance he exercised in assessing an inventor's hopes and dreams, often on the basis of unreliable drawings and inadequate technical specifications, Einstein brought to bear on the physics that occupied him. The many-sided thinking his job entailed he described as a veritable blessing. He had the gift of seeing a meaning behind inconspicuous, well-known facts which had escaped everyone else, recalled Albert's friend and fellow theoretical physicist Max Born. It was this uncanny insight into the working of nature which distinguished him from all of us, not his mathematical skill. Einstein knew that his mathematical intuition was not strong enough to differentiate what was really basic from the rest of the more or less dispensable erudition. But when it came to physics, his nose was second to none. Is that a Jewish reference? I'm kidding. Einstein said he learned to scent out that which was able to lead to fundamentals and to turn aside from everything else, from the multitude of things that which clutter up the mind and divert it from the essential. His years at the patent office only heightened his sense of smell. As with the patents that inventors submitted, Einstein looked for subtle flaws and inconsistencies in the blueprints of the workings of nature put forward by physicists. When he found such a contradiction in theory, Einstein probed it ceaselessly until it yielded a new insight resulting in its elimination or an alternative where none had existed before. His heuristic principle that light behaved in certain instances as if it was made up of a stream of particles, light quanta, was Einstein's solution to a contradiction at the very heart of physics. And then I'll take a break. Brother, I have 20 more pages. I'm probably just demolishing my voice by doing this and nothing else. Oh boy. Let's go. Einstein had long accepted that everything was composed of atoms and that these discrete, discontinuous bits of matter possessed energy. The energy of a gas, for example, was the sum total of the energies of the individual atoms for which it was made up. The situation was entirely different when it came to light. According to Maxwell's theory of electromagnetism, or any wave theory, the energy of a light ray continuously spreads out over an ever-increasing volume, like the waves radiating outwards from the point where a stone hits the surface of a pond. Einstein called it a profound formal difference and made him feel uneasy while stimulating his many-sided thinking. He realized that the dichotomy between the discontinuity of matter and the continuity of electromagnetic waves would dissolve if light was also discontinuous or made up of quanta. The quantum of light emerged out of Einstein's review of Planck's derivation of the black-body radiation law. He accepted that Planck's formula was correct, but his analysis revealed what Einstein has always suspected. Planck should have arrived at an entirely different formula. However, since he knew the equation he was looking for, Planck fashioned his derivation to get it. Einstein worked out exactly where Planck had gone astray. In his desperation to justify his equation that he knew to be in perfect agreement with the experiments, Planck had failed to consistently apply the ideas and techniques he used or that which were available to him. If he had done so, Einstein realized that Planck would have obtained an equation that did not agree with the data. Lord Rayleigh had already proposed this other formula in June 1900, but Planck had taken little, if any, notice of it. At the time, he did not believe in the existence of atoms and therefore disapproved of Rayleigh's use of the equipartition theorem. Atoms are free to move in only three ways: up and down, back and forth, and side to side. Called a degree of freedom, each is an independent way in which an atom can receive and store energy. In addition to these three kinds of translational motion, a molecule made up of two or more atoms has three types of rotational motion about the imaginary axes joining the atoms, giving a total of 6 degrees of freedom. According to the equipartition theorem, the energy of a gas should be distributed equally among its molecules and then divided equally among the different ways in which a molecule can move. Rayleigh employed the equipartition theorem to divide up the energy of a black-body radiation among the different wavelengths of radiation present inside a cavity. It had been a flawless application of the physics of Newton, Maxwell, and Boltzmann. Aside from a numerical error that was later corrected by James Jeans, there was a problem with what became known as the Rayleigh-Jeans law. Ray-Bans, Jeans law. Interesting. It predicted a buildup of an infinite amount of energy in the ultraviolet region of the spectrum. It was a breakdown of classical physics that many years later, in 1911, was dubbed the ultraviolet catastrophe. Thankfully, it did not actually happen, for a universe bathed in a sea of ultraviolet radiation would have made human life impossible. Einstein had derived the Rayleigh-Jeans law on his own and knew that the distribution of black-body radiation that it forecast contradicted the experimental data and led to the absurdity of an infinite energy in the ultraviolet. Given that the Rayleigh-Jeans law tallied with the behavior of black-body radiation and only at long wavelengths or very low frequencies, Einstein's point of departure was Wilhelm Wien's earlier black-body radiation law. It was the only safe choice, even though Wien's law managed to replicate the behavior of black-body radiation only at short wavelengths and failed at longer wavelengths of the infrared. Yet it had certain advantages that appealed to Einstein. He had no doubts about the soundness of its derivation, and it perfectly described at least a portion of the black-body spectrum to which he would restrict his argument. Einstein devised a simple but ingenious plan. A gas is just a collection of particles, and in thermodynamic equilibrium, it is the properties of these particles that determine, for example, the pressure exerted by the gas at a given temperature. If there were similarities between the properties of black-body radiation and the properties of a gas, then he could argue that electromagnetic radiation is itself particle-like. Einstein began his analysis with an imaginary black body that was empty, but unlike Planck, he filled it with gas particles and electrons. The atoms in the walls of the black body, however, contained other electrons. As the black body is heated, they oscillate with a broad range of frequencies, resulting in the emission and absorption of radiation. Soon the interior of the black body is teeming with speeding gas particles and electrons, and the radiation emitted by the oscillating electrons. After a while, thermal equilibrium is reached, when the cavity and everything inside it is at the same temperature T. The first law of thermodynamics, that energy is conserved, can be translated to connect the entropy of a system to its energy, temperature, and volume. It was now that Einstein used this law, Wien's law, and Boltzmann's ideas to analyze how the entropy of blackbody radiation depended on the volume it occupied without establishing any model for the emission or propagation of radiation. What he found was a formula that looked exactly like one describing how the entropy of a gas made up of atoms is dependent on the volume it occupies. Blackbody radiation behaved as if it was made up of individual particle-like bits of energy. Blackbody radiation behaved as if it was made up of individual particle-like bits of energy. And Einstein had discovered the quantum of light without having to use either Planck's blackbody radiation law or his method. In keeping Planck at arm's length, Einstein wrote the formula slightly differently, but it meant and encoded the same information as E equals hv, that the energy is quantized, that it only comes in units of hv. Whereas Planck had only quantized the emission and absorption of electromagnetic radiation so that his imaginary oscillators would produce the correct spatial distribution of blackbody radiation, Einstein had quantized electromagnetic radiation, and therefore light itself. The energy of a quantum of yellow light was just Planck's constant multiplied by the frequency of yellow light. By showing that electromagnetic radiation sometimes behaves like the particles of gas, Einstein knew that he had smuggled his light quanta in through the back door, by analogy. To convince others of the heuristic value of his new point of view concerning the nature of light, he used it to explain a little understood physics phenomenon. The German physicist Heinrich Hertz first observed the photoelectric effect in 1887 while in the middle of performing a series of experiments that discovered the existence of electromagnetic waves. By chance, he noticed that the spark between two metal spheres became brighter when one of them was illuminated by ultraviolet light. After months of investigating the completely new and very puzzling phenomenon, he could offer no explanation but believed incorrectly that it was confined to the use of ultraviolet light. Naturally, it would be nice if it were less puzzling, Hertz admitted. However, there is some hope that when this puzzle is solved, more new facts will be clarified than if it were easy to solve. It was a prophetic statement, but one that he never lived to see fulfilled. He died tragically young at the age of 36 in 1894. It was Hertz's former assistant, Philipp Lenard, who in 1902 deepened the mystery surrounding the photoelectric effect when he discovered that it also occurred in a vacuum when he placed two metal plates in a glass tube and removed the air. Connecting the wires from each plate to a battery, Lenard found that a current flowed when one of his plates was irradiated with ultraviolet light. The photoelectric effect was explained as the emission of electrons from the illuminated metal surface. Shining ultraviolet light onto the plate gave some electrons enough energy to escape from the metal and cross the gap to the other plate, thereby completing the circuit to produce a photoelectric current. However, Lenard also found facts that contradicted established physics. Enter Einstein and his quantum of light. It was expected that increasing the intensity of a light beam by making it brighter would yield the same amount of electrons from the metal surface, but with each having more energy. Lenard, however, found that the exact opposite had occurred. A greater number of electrons were emitted with no change in their individual energy. Einstein's quantum solution was simple and elegant. If light is made up of quanta, then increasing the intensity of the beam means that it is now made up of a greater number of quanta. A more When a more intense beam strikes the metal plate, the increase in the number of light quanta leads to a corresponding increase in the number of electrons being emitted. Leonard's second curious discovery was that the energy of the emitted electrons was not governed by the intensity of the light beam, but by its frequency. Einstein had found a ready answer. Since the energy of a light quantum is proportional to the frequency of the light, a quantum of red light, or low frequency, has less energy than one of blue light, high frequency. Changing the color or frequency of light does not alter the number of quanta in beams of the same intensity. So, no matter what the color of light, the same number of electrons would be emitted since the same numbers of quanta strike the metal plate. Let me just... There we go. However, since different frequencies of light are made up of quanta of different energies, the electrons that are emitted would have more or less energy depending on the light used. Ultraviolet light would use electrons with a greater maximum kinetic energy than those emitted by a quantum of red light. Though there was another intriguing feature. For any particular metal, there was a minimum or threshold frequency below which no electrons were emitted at all, no matter how long or intensively the metal was illuminated. However, once this threshold was crossed, electrons were emitted no matter how dim the beam of light. Einstein's quantum of light supplied the answer once again as he introduced a new concept, the work function. Einstein envisaged the photoelectric effect as the result of an electron acquiring enough energy from a quantum of light to overcome the forces holding it within the metal surface and to escape. The work function, as Einstein labeled it, was the minimum energy an electron needed to escape from the surface, and it varied from metal to metal. If the frequency of light is too low, the light quanta will not possess enough energy to allow an electron to break the bonds that keep it bound within the metal. Einstein encoded all this in a simple equation. The maximum kinetic energy of an electron emitted from a metal surface was equal to the energy of the light quanta absorbed minus the work function. Using this equation, Einstein predicted that the graph of the maximum kinetic energy of the electrons versus the frequency of light used would be a straight line beginning at the threshold frequency of the metal. The gradient of the line, irrespective of the metal used, would always be exactly equal to Planck's constant h. Gradient means slope. Okay. Oh, my throat actually fucking hurts. I spent 10 years of my life testing that 1905 equation of Einstein's, and contrary to all my expectations, complained the American experimental physicist Robert Millikan, I was compelled to assert its unambiguous verification in spite of its unreasonableness, since it seemed to violate everything we know about the interference of light. Although Millikan won the 1923 Nobel Prize partly in recognition of his work, even in the face of his own data, he balked at the underlying quantum hypothesis. The physical theory upon which the equation is based is totally untenable. From the very beginning, physicists at large had greeted Einstein's light quanta with similar disbelief and cynicism. A handful wondered if light quanta existed at all, or whether they were simply a useful fictional contrivance of practical value in calculations. At best, some thought that light, and therefore all electromagnetic radiation, did not consist of quanta, but only behaved as such when exchanging energy with matter. Foremost among them was Planck. When in 1923 he and 3 others nominated Einstein for membership of the Prussian Academy of Sciences, they concluded their testimonial by trying to excuse his light quanta proposal. In sum, it can be said that among the important problems which are so abundant in modern physics, there is hardly one in which Einstein did not take a position in a remarkable manner. That he might sometimes have overshot the target in his speculations, as for example his light quantum hypothesis, should not be counted against him too much, because without taking a risk from time to time it is impossible, even in the most exact natural science, to introduce the real innovations. 2 years later, Millikan's painstaking experiments made it difficult to ignore the validity of Einstein's photoelectric equation. By 1922, it was becoming almost impossible, as Einstein was belatedly awarded the 1921 Nobel Prize for Physics explicitly for his photoelectric effect. For his photoelectric effect law, described by his formula, and not for his underlying explanation using light quanta. No longer the unknown patent clerk in Bern, he was by then world famous for his theories of relativity and widely acknowledged as the greatest scientist since Newton. Yet his quantum theory of light was just too radical for physicists to accept. And then we take a break. This shit is doing wonders for my throat. And by wonders, I mean it is absolutely fucking it up. How long until the next break? Okay, it's at 61, we're at 52. Ooh, man. I'll take a longer break because that's a lot of pages, man. Oh, I'm gonna rake your Vic. I swear. Alright. The stubborn opposition to Einstein's idea of light quanta rested on the overwhelming evidence in support of a wave theory of light. However, whether light was a particle or a wave had been hotly disputed before. During the 18th century and in those early years of the 19th, it was Isaac Newton's particle theory that had triumphed. My design in the book is not to explain the properties of light by hypotheses, Newton wrote at the beginning of Optics, published in 1704, but to propose and prove them by reason and experiments. Those first experiments were conducted in 1666, when he split light into the colors of the rainbow with a prism and wove them back together into white light using a second prism. Einstein believed that rays of light were composed of particles, or as he called them, corpuscles, the very small bodies emitted from shining substances. With the particles of light traveling in straight lines, such a theory would, according to Newton, explain the everyday fact that while a person can be heard talking around a corner, they cannot be seen since light cannot bend around corners. Newton was able to give a detailed mathematical account for a host of optical observations, including reflection and refraction. the bending of light as it passes from less to a more dense medium. However, there was other properties of light that Newton could not explain. For example, when a beam of light hit a glass surface, part of it passes through and the rest was reflected. The question Newton had to address was why some particles of light were reflected and others not. To answer it, he was forced to adapt his theory. Light particles caused wave-like disturbances in the ether. These fits of easy reflection and easy transmission, as he called them, were the mechanism by which some of the beam of light was transmitted to the glass and the remainder reflected. He linked the bigness of these disturbances to color. The biggest disturbances, those having the longest wavelength, in the terminology that came later, were responsible for producing red. The smallest, those having the shortest wavelength, produces violet. The Dutch physicist Christian Huygens argues that there was no Newtonian particle of light. 13 years older than Newton, by 1678, Huygens had developed the wave theory of light that explained reflection and refraction. However, his book on the subject, Traité de la Lumière, was not published until 1690. Huygens believed that light was a wave traveling through the ether. It was akin to the ripples that fanned out across the still surface of a pond from a dropped stone. If light was really made up of particles, Huygens asked, then where was the evidence of collisions that should occur when two beams of light crossed each other? There was none, argued Huygens. Sound waves do not collide, ergo light must also be wave-like. Although the theories of Newton and Huygens were able to explain reflection and refraction, each produced different outcomes when it came to certain other optical phenomena. None could be tested with any degree of precision for decades. However, there was one prediction that could be observed. A beam of light made of Newton's particles traveling in straight lines should cast sharp shadows when striking objects, whereas Huygens waves, like water waves bending around an object they encounter, should result in shadows whose outline is slightly blurred. The Italian Jesuit and mathematician Father Francesco Grimaldi christened this bending of light around the edge of an object, or around the edges of an extremely narrow slit, diffraction. In a book published in 1665, 2 years after his death, he described how an opaque object placed in a narrow shaft of sunlight allowed to enter an otherwise darkened room through a very small hole in a window shutter, cast a shadow larger than expected if light consisted of particles traveling in straight lines. He also found that around the shadow were fringes of color, light, and fuzziness, where there should have been a sharp, well-defined separation between light and dark. Newton was well aware of Grimaldi's discovery and later conducted his own experiments to investigate diffraction, which seemed more readily explicable in terms of Huygens' wave theory. However, Newton argued that diffraction was the result of forces exerted on light particles and indicative of the nature of light itself. Given his preeminence, Newton's particle theory of light, though in truth a strange hybrid of particle and wave, was accepted as the orthodoxy. It helped that Newton outlived Huygens, who died in 1695, by 32 years. Nature and nature's laws lie hid in night. God said, "Let Newton be," and all was light. Alexander Pope's famous epitaph bears witness to the awe in which Newton was held in his own day. In the years after his death in 1727, Newton's authority was undiminished, and his view on the nature of light barely questioned. At the dawn of the 19th century, the English polymath Thomas Young did challenge it, and in time his work led to a revival of the wave theory of light. Oh, my throat, it hurts. It hurts. Born in 1773, Young was the eldest of 10 children. He was reading fluently by the age of 2 and had read the entire Bible twice by 6. A master of more than a dozen languages, Young went on to make